Now we will continue our study with nonlinear inequalities and look at rational inequalities. So just like polynomial inequalities, we define a rational inequality to be an inequality of the form f of x is greater than 0, f of x is less than 0, f of x is greater than or equal to 0, or f of x is less than or equal to 0, where f is a rational function. Solving rational inequalities is actually very similar to solving polynomial inequalities. We can use a graphical or algebraic method to solve those inequalities. The only difference, though, is that we need to determine the restrictions on the variable of a rational function. And recall, restrictions are values that make the denominator 0, right, where that function is undefined. And because these values are not in the domain of the rational function, they cannot be in the solution set of a rational inequality. So we will follow basically the same steps that we've done before. We'll rewrite the inequality so that one side is 0. Then we will find the zeros of the function by solving the equation f of x equals 0, that is that associated equation. And we'll also find the restrictions on the variable, those values that make the denominator 0. And the restrictions and zeros are called the boundary numbers. We'll place the boundary numbers on a number line to determine the test intervals. We can test a point from each interval in the original inequality to determine if the test point satisfies that inequality, or we can also use a graph to determine where solutions are located. We'll then determine which intervals satisfy the inequality, determine if the zeros are included or not, but remembering that the restrictions will never be included, and then we'll write the solution set in interval notation. So I will do a couple of examples here with you. We want to solve the inequality 4 minus x divided by the expression x plus 5 is greater than or equal to 2. And so we're thinking about solving 4 minus x all divided by x plus 5 minus 2 is greater than or equal to 0. So that is, we want to find values of x that make this function, this rational function, positive or 0. Things we need to do, we first need to find the boundary numbers. And the boundary numbers come from solving where we replace the inequality sign with an equal sign, so we get the expression 4 minus x divided by x plus 5 minus 2 is equal to 0. And we can solve that rational equation by multiplying each side by the least common denominator of x plus 5. And so when we do that, we would get x plus 5 times expression 4 minus x, all divided by x plus 5, minus 2 times x plus 5 is equal to 0 times x plus 5. Simplifying, we just get 4 minus x. Then distributing the negative 2 gives us minus 2x minus 10 equals 0. We can combine like terms. Negative x minus 2x is negative 3x. 4 minus 10 is minus 6 equals 0. We can add 6 to get negative 3x equals 6 and divide by negative 3 to get negative 2. That value is our 0. We also need to find the restriction, and the restriction is where the function is undefined, and that is where the denominator x plus 5 is equal to 0, and that is at negative 5. So we want to place both of these boundary numbers on our number line. We place negative 5 and then negative 2, and this subdivides the number line into 3 regions, A, B, and C. Our region from A is the interval negative infinity to negative 5. In region B, the interval is between negative 5 and negative 2. And in region C, our interval is from negative 2 to infinity. We can choose the test point in region A, something to the left of negative 5, so we'll say negative 6. In region B, between -5 and -2, so maybe we'll use -3. And in region C, a number greater than -2, because 0 is in that region, we'll choose 0. Testing, we plug into this inequality. 4 minus x divided by x plus 5 minus 2 is greater than or equal to 0. So we would say 4 minus -6 all divided by -6 plus 5, and then minus 2, is that greater than or equal to 0? So 4 minus 6 is 4 plus 6, or 10, divided by -6 plus 5 is -1. So 10 divided by -1 is -10 minus 2. Is that greater than or equal to 0? Well, no, that's -12, which is not greater than or equal to 0, so this will be false. Substituting -3 in for x, we get 4 minus, in parentheses, -3, divided by -3 plus 5, minus 2. Is this greater than or equal to 0? So 4 minus 3 is 7, divided by -3 plus 5 is 2, so that's 7 halves. 7 halves as a decimal is 3.5. Minus 2, is that greater than or equal to 0? Yes, this is 1.5, which is greater than or equal to 0, so this is true. And then lastly, we substitute 0. 4 minus 0 divided by 0 plus 5 minus 2, is that greater than or equal to 0? Well, this is 4/5, or 0.8. Minus 2, is that greater than or equal to 0? No, that's -1.2, which is not greater than or equal to 0, so this is false. So solutions of this inequality lie in region B, and so we're going to shade our number line between the -5 and the -2. And then this is where we need to be very careful. We are permitted to also include the zeros, right, where we can equal 0. And so we want to include the value that was our 0, which is -2. So we can put a bracket at the -2. But remember, -5 is a restriction. X cannot be -5 because it makes the denominator 0, so we cannot include that in the solution set. So we actually need to have a parenthesis on the -5, but a bracket on the -2. So the solution set for this inequality is a open parenthesis at -5, comma, -2, close bracket. Now, just like with the polynomial inequalities, we can use a graph. This is not one of our basic transformations that we've looked at, so what I've done, think about setting this function 4 minus x divided by x plus 5 minus 2 greater than or equal to 0. So our f of x, that is our rational function, is the 4 minus x divided by x plus 5 minus 2. I've input this on the graphing calculator, and just be careful when you do this that you input the numerator and denominator of the fraction in parentheses. So I have parentheses 4 minus x, close parentheses, divided by, in parentheses, the expression x plus 5, and then minus 2 in for y1, and then I graphed this. So remember that what we see are two different pieces, two branches, so to speak. At -5, we have this vertical asymptote. Again, these aren't going to be drawn on your graph. You've got to remember that there is a vertical line there at which the graph cannot cross. And then we also have a 0 at this point, -2, 0. And so this -5 and -2 on the x-axis actually subdivide our number line and our graph into parts where it's going to be all below or all above the x-axis. And so if we think about placing this -5 and -2 on the number line that I have drawn on the screen, then we see that to the left of -5, the graph is all below the x-axis. Between the -5 and -2, the graph is all above the x-axis. And to the right of -2, the graph is below. So we want to find where this function is greater than or equal to 0, which corresponds to the part of the graph that is above or on the x-axis. So that means we can include the interval between the -5 and -2, and also the -2 because it is where the graph is on the axis. But at the -5, we cannot include that. Now, again, I could also use a table from my graphing calculator. If I input the function and look at the table, remember that the -5 and the -2 are going to subdivide this table really into 3 pieces. Everything to the left of -5, between -5 and -2, and everything to the right of the -2. And to the left of -5, we see that all those function values are negative. So it is not positive in that particular interval. Between the -5 and -2, we see positive y values, right? So those are x values that have positive output values. And to the right of -2, we see negative y values again. So the only region that gave us positive y values was between the -5 and -2. Now you can also see on the table that at -5 we get an error message, so hopefully that would remind you that I cannot include the -5 in the solution set. -2 is where we get the y value of 0, so we are permitted to include that since our inequality sign is greater than or equal to 0. Now we have this inequality, the expression p squared minus 2p minus 8, all divided by p minus 1, is greater than 0. And so to solve this by hand, we first want to think about finding the boundary numbers. So to find the boundary numbers, we'll solve this equation, p squared minus 2p minus 8, all divided by p minus 1 equals 0. And we can solve this by multiplying by the least common denominator of p minus 1. And when we multiply each side by that, we are left with p squared minus 2p minus 8 is equal to 0. So we have a quadratic equation that we can solve by factoring. The factors of p squared minus 2p minus 8 are p minus 4 and p plus 2. So we can set those factors equal to 0 to get p minus 4 equals 0 or p plus 2 equals 0. Therefore, we have solutions of 4 and -2. So those are the boundary numbers that are zeros of this function, of this rational function. We also have the restriction, and the restriction comes from what value makes the denominator 0. And that is where p minus 1 is equal to 0 or p is equal to 1. So we place the zeros and the restriction on the number line in order from smallest to largest, so that gives us -2, then 1, and 4. These 3 boundary numbers subdivide our number line into 4 regions, A, B, C, and D. So in region A, we have the interval from -infinity to -2. Region B is from -2 to 1. Region C is from 1 to 4. And then region D is from 4 to infinity. So our test point in region A can be p equals -3. We plug into the original inequality to get -3 squared minus 2 times -3 minus 8, all divided by -3 minus 1, and we want to see if this is greater than 0. So simplifying the numerator, we get 9 plus 6, which is 15, minus 8 is 7, divided by -3 minus 1 is -4. Is this greater than 0? Well, that's a negative 7/4, which is not greater than 0, so this would be false. In interval B, between negative 2 and 1, we're going to choose our favorite number, 0, and we would get 0 squared minus 2 times 0 minus 8 divided by 0 minus 1. Is this greater than 0? Simplifying the numerator, we get negative 8 divided by negative 1. Is that greater than 0? Well, yes, because negative 8 divided by negative 1 is positive 8, which is greater than 0, so that is true. Then in region C, a number between 1 and 4, we'll choose our p-value of 2. So we would have 2 squared minus 2 times 2 minus 8, all divided by 2 minus 1. Is this greater than 0? This simplifies to 4 minus 8, which is negative 8. Divided by 2 minus 1 is 8. But negative 8 divided by 1 is negative 8, which is not greater than 0, so that is false. And lastly, in region D, we will choose our value of 5. And so we get 5 squared minus 2 times 5 minus 8, all divided by 5 minus 1. Is that greater than 0? So that's 25 minus 10, or 15, minus 8 is 7, divided by 5 minus 1 is 4. Is that greater than 0? And yes, it is. So that's true. And so our solutions of this inequality are the regions that tested true, which are regions B and D. So we're going to shade the region between negative 2 and 1. We'll shade the region to the right of 4. And then we need to figure out what happens on these endpoints. Well, since we're strictly greater than 0, we cannot include the zeros of negative 2 and 4. But also, we can never include our restriction of 1. Therefore, we have parentheses on all of these endpoints. And so our solution set in interval notation is negative 2 to 1 in parentheses, union parentheses 4 to infinity. Now, I also want to illustrate how we can use a graphing calculator to help us solve this inequality. I've entered on the calculator this rational function. So I'm letting y1 equal, because we have to use x, we're going to change the variable p to x. So this would be x squared minus 2x minus 8, all divided by x minus 1, being sure that on the calculator we put the numerator and denominator in parentheses. And then we're going to graph. Recall that we had zeros of negative 2 and 4, and we also had a restriction at 1, right? So x cannot equal 1. So we had a vertical asymptote at x equals 1, and then we had a 0 at negative 2 and a 0 at 4. And so if I think about now the x-axis as my number line, I'm going to put negative 2, 1, and 4 on the number line. And we see these 4 regions. So we have to the left of negative 2, let's think what happens. To the left of negative 2, the graph is all below the x-axis. Okay. Between negative 2 and 1, the graph is above the x-axis. Between 1 and 4, the graph is below the x-axis. And to the right of 4, the graph is all above the x-axis. So remember that for us to find the values of x for which the rational function is greater than 0, that is, the output value is positive, we need to find where the graph is above the x-axis, and that is indeed just what we found algebraically between the negative 2 and 1 and to the right of 4. And again, we cannot include the zeros, so we have a parentheses on the negative 2 and the 4. We can never include the restriction of 1, so that's confirming what we just found there. So I also copied over the table from the graphing calculator for this particular function. And again, I see that my 0 of -2 is showing up, right? The y value is 0 there. The restriction of 1 has an error in the y column. And then the 0 of 4 has a 0 in the y column. So again, I can think about these as where my number line gets subdivided and think about what happens to the y values around those numbers. And so to the left of -2, the y values are negative, which don't satisfy the inequality. Between the -2 and 1, the y values are positive, which do satisfy the inequality. And then between the 1 and 4, the y values are negative, and greater than 4, the y values are positive.